Hello, my name's Gabe. For this problem, we want to use Stokes Theorem to evaluate this integral, where f is given by 2yi plus 3zj plus xk, and we know that C is a triangle with vertices at 2, 0, 0, 0, 2, 0, and 0, 0, 2. So Stokes Theorem actually says that this integral that we're looking for is equal to this double integral over surface S, so the surface integral, of this curl of f dotted with some vector which is normal to our surface n times ds. So our first step should be to go ahead and find the curl of f. So the curl of f is equal to the determinant form of this, whose first row is I, j, k. The second row is the partial derivative with respect to x, partial derivative with respect to y, and the partial derivative with respect to z. So we'll view the second row as operations. And then the third row is going to come from our function f. So we'll have 2y in the first column. We'll have 3z in the second column. And in the third column, we'll have x. So now we can go ahead and we can write out what the curl is. So for the I part, we're going to have the partial derivative of x with respect to y, which is 0, minus the partial derivative of 3z with respect to z, which is 3. We'll multiply this by I. Now for the j part, we're going to be subtracting the partial derivative of x with respect to x, which is 1, minus the partial derivative of 2y with respect to z, which is 0, and we're multiplying that by j. And finally, we have the k part, so we'll have the partial derivative of 3z with respect to x, which is 0, minus the partial derivative of 2y with respect to y, which is 2, and we're multiplying this by k. So what we see is we see that the curl of f is equal to negative 3i minus j minus 2k. So there's the curl of f. So now our goal should be to find this vector n. So this vector n is going to be normal to this triangle with these three vertices. So what we want to do is we want to find a plane that passes through those 3 points. And if we play around with that a little bit, the plane that we'll find is x plus y plus z equals 2. Now you can verify that these 3 points lie in this plane. It's pretty easy to do. Substitute 2 in for x, 0 for y and z, we get 2 equals 2. Verify that 0, 2, 0 is in this plane, substituting 0 for x and z, and 2 for y, and we have 2 equals 2. And the same thing for the point 0, 0, 2. Substitute 0 in for x and y, 2 in for z, and we have 2 equals 2. So this right here is the plane which contains the 3 points or the 3 vertices of our triangle. So what we'll want to do here is we want to solve for z so that we can obtain our g of xy. Now solving for z is pretty easy. We're just going to subtract x and y from both sides of this equation. So we have z is equal to 2 minus x minus y. So now that we have this g function, we can go ahead and we can write down what our normal vector is. So n is going to be equal to the negative partial derivative of g with respect to x times I minus the partial derivative of g with respect to y times j plus k. So now looking at g, we see that the partial derivative of g with respect to x is negative 1. So this will be negative 1 times I, which is just I. The partial derivative of g with respect to y is also negative 1. So this will be plus j. And finally, we'll have plus k. So now we can take this idea back to finding this integral here. So we have the integral over c of f dotted with dr is going to be equal to the dot product of our curl, which was negative 3i minus j minus 2k, with this vector n, which is I plus j plus k. And the differential here is ds. So now we'll go ahead and we can find this dot product. And working through finding this dot product, what we'll find this is equal to is going to be negative 6. And at this stage, we can replace the surface integral with a double integral over some region in the xy plane. And as I said, this dot product ends up being negative 6, as it's negative 3 times 1, minus 1 times 1, minus 2 times 1 is negative 6. And as I said, we now change this to a double integral. So now we see that this negative 6 is just a constant, and we can pull this out in front of the integral. And we're integrating over a region in the xy plane. And all that we're integrating is dA. So something that you might want to notice here is that we can go ahead and we can actually find what the area is that we're integrating over and what the region is and perform this integral. But if we just sketch a quick picture of what these 3 points or what these 2 points are going to give us in the xy plane, we know that we have the point 2, 0, 0, and we have the point 0, 2, 0. So in the xy plane, these 2 points are going to look like this, and the trace in the xy plane is going to be a triangle. So now, if we're looking at this and we want to compare it to this integral, all that we have to say is that this integral right here is the area of this triangle. So now all we need to do is calculate this area, which is pretty simple to do. So we see that the base is 2, the height is 2, so the area of this triangle is going to be 1/2 times 2 times 2, which is just 2. So this is negative 6 times 2, which is equal to negative 12. So what that tells us is that this integral is equal to negative 12. Thank you.